A single line of missing code can bring down an entire backend architecture. Forget to close an open file or release a database connection, and the resulting memory leak creates intense, compounding pressure on the system. Typically, a function opens a resource, completes its work, and closes it. But if the system encounters an unexpected error or a panic right in the middle of that process, the function exits early. That final close command never executes. Older languages try to catch these errors using nested try, catch, and finally blocks. You end up with code pushed so far to the right of the screen, it becomes nearly impossible to read and maintain. Go uses a single keyword to solve this: defer. By typing defer right next to the code that opens the resource, you guarantee the cleanup task will execute the exact moment the function finishes, no matter how it exits. You handle the teardown at the exact same time you write the setup. A missed cleanup is no longer a possibility, because the safety net is built directly into the foundation of the code. Writing the cleanup code directly next to the setup code creates an interesting mechanical timeline. The cleanup instruction sits near the top of your file, but the actual execution is delayed until the very end of the function's lifespan. When you write multiple defer statements, Go doesn't run them immediately. It pushes each onto an execution stack. This strict last-in, first-out structure empties in reverse order when the function returns. The last task deferred executes first. There is a specific mechanical trap here: immediate argument evaluation. Defer captures the exact values of variables at the exact moment it is declared. If those variables change later in the function, the deferred task ignores the updates and uses the original snapshot. This makes defer a strictly mathematical timeline manager. By locking in both the execution order and the variable states up front, it prevents race conditions during the teardown process. Despite how reliable the system is, for years, experienced Go engineers actively avoided using defer in high-speed, performance-critical loops. Before Go version 1.14, every single defer statement required the system to carve out memory on the heap and track the task using a linked list. In a tight loop, that runtime overhead quickly bogged down the CPU. Then, the Go team rewrote the compiler. They introduced a feature called open-coded defers, which allows the compiler to mathematically prove when these deferred tasks are static and safe. Instead of managing a complex list at runtime, the compiler secretly pastes the cleanup code directly into the function's exit paths. It completely bypasses the memory allocation step. The language designers chose to enforce safe, correct code structure from day one. Once that standard was set, they optimized the compiler under the hood, ensuring engineers would never have to sacrifice speed for reliability. You see the full power of this mechanical guarantee in concurrent programming, specifically when managing a mutex, a tool that locks a piece of data so only one process can read or write to it at a time. If a piece of code locks that data but fails to unlock it due to an error, you trigger a system-wide deadlock. Every other operation waiting for access is permanently frozen out. By pairing the lock command immediately with the defer unlock, you secure the exit door the moment you walk in. Even if the internal logic panics and crashes, the system will forcibly release the lock on its way down. This identical pattern is used to cleanly sever open network connections and automatically roll back failed database transactions before they can corrupt data. This approach keeps the codebase perfectly flat and readable. By moving the teardown instructions to the top, the logic becomes structurally immune to the chaos of unpredictable exits.